Hi, everyone. Thanks for joining the webinar today. I know that it's a tricky time of the academic year with graduations and summer and finals and all that, but hopefully this is a useful update to uh, what we can offer through your EGI EEG system. So today we're going to be talking about our additions to lab streaming layer and open source tools. And Isaac, if you can go to the next slide. So basically, what we're trying to do here is combine what you can do currently with your high density EEG system, where you might need precise resolution to discover new markers in EEG, quantify networks, quantify dynamic activity across different brain areas, and have good coverage for that, or define targets for neuromodulation. And then also just the logistical things of including more people and hair types with our specific sensor nets that are optimized for that, or just doing quick recordings where you need a density of recordings without a long setup time. So if you want examples of publications currently using either high density EEG or searching down into something like BCI or closed loop applications. Our new EGI.com publications searchable library allows you to filter based on EEG, TMS, other modalities that you might be interested in, or combinations of the two. And really, it's a really useful tool, even adding beyond what you can do in kind of Google Scholar or other tools like that. Uh, on the next slide, just two papers that are kind of nice overviews of where high density EEG can provide extra value in, say, like a BCI or other things. They're nice starting points, but feel free to search the publications library for additional resources in your topic area. And all of this is today we're going to be talking about is built off the platform that you're probably using, the GES 400. But we're also doing this in as we've recently launched our GES 500 and NetStation 6 software. And that combination of hardware and software is going to allow you to use everything that we're showing today for these closed loop and other more advanced open source applications, as well as integrating more hardware to make syncing and interacting with everything that you want to do much easier. So we have a variety of new ports that easily accept or send out TTL pulses to sync things. We have a variety of options to sync different devices. Uh, Today, we'll be going over the improvements in lab streaming layer and then also the traditional network-based connectivity. And we should reiterate that we still use NetStation for a variety of approved research and clinical workflows for acquisition of EEG and visualizing high density EEG in particular, as not all tools are able to render high density EEG at the same level or ability or in multiple views. So we see these as two symbiotic kind of options for being able to do high density EEG work. So today, I'll turn it over to Isaac from our application support team. He's based in the Netherlands, and you may have had a chance to meet him in your lab or in just interacting with support team. And this is going to be the first of several webinars where we're getting our application support team to show off the work that they've been doing to build more documentation and support and test some of these more open source tools so that we can support all of you in doing the important work that you're doing. So with that, I'll turn it over to Isaac.
Hello, everyone. Thank you, Trey, for the introduction. So, yeah, my name is Isaac. I'm the application product support specialist for EGI. So today I will be walking you through the latest updates to this LSL EGI AmpServer Connector and our lab streaming layer integration for real-time data access from any of your amplifiers through the AmpServer Pro SDK. So with this update, the main goal has been to make real-time data streaming more accessible, whether you are working on closed-loop applications, maybe neural feedback or VCI research. We've tried to simplify the workflow so that more people can incorporate these tools into their work, regardless of your technical background. So first of all, I wanted to start with why lab streaming layer. So for any of you wondering, this framework has become a standard in neuroscience and human-computer interaction research. So this, as mid of 2025, there's been LSL has been cited over 2,300 times in scientific articles, and this number is growing still steadily. And with many of you are probably already using it now. So LSL, just as an overview, supports a long list of devices from physiological streams like EEG to eye tracking, motion capture, sorry, stimulus markers, and many other hardware devices. And on the software side, it works across all major programming languages, operating systems, and integrates directly with many other open source tools that researchers are already using. So its main advantage is how it handles synchronization across all of those hardware devices and these multiple streams on the network. So it's basically getting these multiple devices to agree on time, which is generally difficult. And LSL solves that by using this network time protocol, which continuously corrects for clock offsets and drift with no dedicated hardware or complex manual configurations needed. So for us, choosing LSL is really about giving our high density EG users an easy access to all of that. So you're able to connect your amplifiers to whatever other hardware you or software you might be wanting to use, and also allowing you an easy way to access the data in real time. So before we actually dive into the actual connector and the applications that you can use with the LSL interface, I'm going to start with a quick overview of what the SDK is. So the SDK is our software development kit for the AmpServer Pro, and it's wanna can introduce this to then link it to how LSL helps on all of this. So the SDK is essentially what allows you to interface directly with your net amps, so the server of your amplifier, and it makes possible to access, record, and visualize basically the data. So it includes a bunch of server-side and high-level APIs, along with network and data protocols that you will need for any kind of custom integration. And it also comes with a few examples that you can either use as is or build on this background on what we provide. And all of these work in different cross Unix, Xcode, and MATLAB environments. So now, well, while you're welcome to go that route and work directly with the SDK, it does require a fair amount of familiarity with these tools, and we provide currently limited support on the SDK side. So that's where exactly LSL comes in. So LSL built specifically for it's built specifically for the synchronization of real-time data streaming, like I said. And what it allows you with this connector is essentially bridge these two things. So the LSL framework with the SDK. So it takes care of all of this communication for you. So instead of having to dig into it directly, you get a straightforward way to start streaming your data. And from there, you can focus on whatever your actual project needs are, regardless of your coding background. So moving forward, I also want to start a bit on what do you need for actually using LSL with our systems. So in terms of requirements, you will need the AmpServer Pro SDK package enabled on your amplifier and a computer with any operating system to actually have the LSL interface downloaded in. So it works across Linux, macOS, and Windows. So if you are interested in getting this enabled on your amplifier, just please feel free to reach out to us at any time, and we can just start this discussion and schedule a time to make this happen. So after the SDK is enabled, you will need to download the LSL EGI AmpServer Connector that's available for free on GitHub. Always make sure to run the latest version, so updates might come with meaningful improvements. So it's important you're just working with the last one. And I will be working through some of these key specs and settings of the connector, of course, today. But I do want to flag that it's important that anyone interested in using this connector to go through the README file in GitHub. This is your best reference for making sure that everything is configured correctly and for your specific setup. And it's worth taking time to go through it carefully before you get started. Once you have your connector running and your data streaming, then you can either pick up one of the existing open source applications that work already with LSL, or you can go ahead and build something more specific for your needs. So we will cover both of these paths a bit later. So we will start more with these open source examples and then on how you can build your own tools. So let's walk through the connector interface. So if you have used previous versions of the connector, the overall structure might look familiar to you, but there are some meaningful updates worth going through. So from top to bottom, we have first the network settings. So in the first line, we have the AmpServer address. That's just going to be your IP of your amplifier, which is mainly only always going to be this 10.10.10.51. The only case you maybe want to change this if you are doing hyperscanning. So if you're using two amps at the same time, you can then run two connectors and then you'll have two different IP addresses. So it's important that you differentiate these amplifiers here. Then after that, you have the command notification and data ports. This is just basically the ports that the SDK uses for the communication through the APIs. So these ones need to be left as default. And yeah, there's not much else to do in this side. So when we move to recording settings, here's where the main differences come compared to the previous app connector that we had available. So the first is the sampling rate. Now we have two different sampling modes, so the decimated and the native. And within these modes, we have up to 8 different sampling rates. So when we are choosing a decimated mode, which offers 250, 500, and 1000 hertz, the data passes through the amplifier's internal FPGA anti-aliasing filters. So it introduces a small delay between when the activity actually occurs and when it appears in the data stream. So that's the same way that it works with NetStation. So some of you might be familiar with this concept. So this is why there's also this align timestamps option, which will compensate for this filter delay as it's done with NetStation. So usually this decimated mode is best for ERP paradigms or third-party recording scenarios, or when you want to synchronize to other external markers from other devices. So it's not ideal for immediate access to the real-time data. So this one you want to use the native mode. So the native mode includes 500 low latency and 1000 low latency, and then the 2400, 4000, sorry, and 8000. So all of these are the low latency options. So these ones bypass the internal filters and samples directly at the requested rate. So it's giving you low latency and making it the right choice for any real-time closed loop PCI applications. When using native mode, the timestamps will tick off automatically, so there's not going to be any alignment done after. And it's important to know that there are some crucial requirements if you're wishing to stream with the LSL connector and NetStation at the same time. So I wanted to bring this up here because it's mainly about the sampling rates. So all of these are explained in the README file, like I said before, but it's important that the sampling rates match between NetStation and the connector if you are wishing to stream with both at the same time. And of course, you cannot really choose the native modes because NetStation doesn't have the option. So if you want to do real-time access to the data, it's better to bypass any need to use NetStation. So moving on, there's also now an automatic sensor layout recognition. So it will detect your hydrocell geodesic sensor net automatically, and it's going to give you access to the channel information. So then you can access it to any LSL app or your own setup. And then another key update is how the connector now opens 3 streams. So when you start streaming, you will have the EGI net AMP51, which is your EEG data, and now it also includes physiological data if you connect a physio, which is automatically detected. Then you have the EGI net AMP51 DIN. So this one is to stream markers from your digital input port of your amplifier. So this is just a marker stream that can be synchronized with your EEG data, and it's what this timestamp alignment will work for. It's to correct the offset between these two. And then we have the notifications one, which is just an optional port, which you will have any notifications like a net has been flagged or other important things that happen that are not related to the data. Finally, there's also now the option to measure impedances directly from LSL, so you don't need to open NetStation, and that makes it ideal for applications where you cannot use NetStation for the sampling rate. So this impedance is just, there's an example script with Python in the README section of GitHub as well, which produces this list of impedances. You're then free to use that to customize your own visualization, either if it's a topographic map or any other thing that you would like to visualize, maybe similar to NetStation with colors. It's free for anyone to use and customize. So that's all the main updates. So how do you actually then link to the AMP server and start streaming? That's really simple steps. You will just select the desired sampling rates based on your desired application. You will then click on the link button and verify that you have here a stream started and a timestamp value. If this doesn't appear, there's some sort of problem. So just double check, maybe restart the app, or feel free to contact us if you also run into any issues. And then just also scroll through all the log so it has more information, just to make sure that every setting that is here, it makes sense for your setup. So you will see here the information of the fuse G16, what sampling rate you're using, whether the amplifier has been initialized correctly, and also if your timestamp alignment is enabled in this case on the right. So it's important to keep this connector window open until you wish to link from the AMP server. So for any work then you do to any other application, just keep this running on the background. And this way you will make sure that the data streams are always available. Here I also want to quickly talk about the importance of Lab Recorder before moving to these open source tools. It's important to highlight it because it's an important piece that sometimes is overlooked. So Lab Recorder is the default recording application from LSL. And once your EGI AmpServer Connector is linked, you will see these streams that I was showing before you here, and any other streams you have from other devices that you might be using as well. They are going to all appear here. So this application runs on the background, and it allows you to record the data, and that's what it's going to then allow you to synchronize the timestamps after prior when you upload this XDF, which this records in XDF format. That then you're going to be able to upload it through M&E, Python, or EGLab, and that will apply the correction. So it's important to have this as your recording interface. It can also be called from any of your codes, so you don't have to do it automatically. I manually, sorry, so you can do it automatically. And this will allow you to just focus on your real-time paradigms, to just focus on the real-time analysis, and then this interface be able to record your data. So now that we have the connector running and lab recording is set up in the background, we can look at what we can actually do with your data streams. So one of the things I want to emphasize here is that you don't necessarily need to build from scratch. There are already well-developed open source tools that integrate directly with LSL and can get you up and running with minimal configuration. So in the next few slides, I will walk you through the 3 concrete examples that we've come up with just to show you how easy it's to interface with some of these applications. So we'll look at this real-time ERP visualization with OpenPipe and ePrime, a neurofeedback example using NeuroPipe pipelines, and a VCI example using available apps from the Medusa interface. So these are just examples. The idea is just to show you how quickly you can go from streaming your data with the app connector to actually doing something meaningful with it. So here we have the first example, which is the real-time ERP visualization. So here we have one of the prime setups that you might have. Also works with other softwares like PsychoToolbox and PsychoPy, of course, among others. So here, these are communicating all via the LSL streams. So as soon as the experiment is started, this sends a notification to the LSL server in these other computers through the network, and it all synchronizes the events coming through the experiment together with the EEG data. So here also in the EEG data, we can see how the events are coming with these dotted lines. And then these ERP plots, which they just take the data. That's just for visualization. It's not really like it's fully processing the data in real time. So it's just doing an averaging, but it could be a good tool to just have something running alongside your experiment to make sure that the participant is engaged, and you want to maybe just visualize how the ERPs are visualizing over time. So here I have a second video, which, oops, sorry. now here, which is later on this experiment. So we can see here later on the video that we now can start clearly see that's an oddball paradigm. So we can start clearly see that the target stimuli has a peak more than this 300 milliseconds after, so typical P300. So you can see how it looks over time, and then just have it as a optional view for your ERP paradigms. Then we have a neurofeedback example here that what I mentioned with neurofeedback. NeuroPipe has an amazing amount of pipelines already created that you can customize yourself, and it's as easy to then set an LSL node that connects to your EGI AmpServer stream or your digital inputs stream as well. So once you call all of this in and you have some minor modifications maybe on the channels and some other things, you can do quite cool things. So here that pipeline, which is here in the background, you cannot really see it. It's processing this data in real time, and it's using the alpha power to feed this Python created thermometer as a neurofeedback application. So here the participant was instructed to relax, to have more alpha power, to increase the thermometer. So this will move up and down depending on the state. And here you can see some other visualizations that you can also create with NeuroPipe really easy. So this maybe I'm going to go through the next here. So here we can see some other visualizations that you can do. For example, these topographic maps were interactive, and you can see the alpha power, for example, in this case in real time. Here's a moment that he was more relaxed, and you see the occipital area was accentuating more power here. And then you also have power spectral density maps and normal time series plot here on the left. So you have many options, and that's just a few examples that I pulled up, and you have a lot of other visualizations that you're welcome to explore, and it's quite easy to set up. And then last, I wanted to show a BCI experiment with the Medusa interface. So here we had this motor imagery experiment where the participant was instructed to imagine to grab something with the right hand or something with the left hand to move the ball to the right or to the left. So this we ran with the participant quite a lot of a long training, and then in the Medusa interface you can also fit these calibration files on a machine learning paradigm, and then it trains the model, and then you can use that trained model to then actually run online and see how this participant is able to perform with these BCI experiments after some trainings and of course some other calibrations. So yeah, we can see that he was, in this case, he was performing quite well. He was actually following the right instructions. And then in the background, we can see that also the Medusa interface allows you to do real-time plots, also in real time with time series plots, also connectivity plots, and they have other options available. Okay, moving on. So those were the ready-to-use tools that we just covered. So they have already been designed, and they are made to already handle an ideal buffer and chunk parameters for real-time applications. So you don't really need to play much with that. There's some configurations in your pipe that you actually need to set these settings, but it's quite interactive. So you don't really have to worry about that with these interfaces. But what if you have more specific needs and you want to build your own custom setups? Then you can maybe use the Python and MATLAB libraries for LSL. And in these next slides, I will walk you through a bit of basics on what it's important for configure these applications. So before we actually dive into that, I want to make sure to spend a few minutes understanding how LSL sends and receives data, because this will directly impact the parameters that you need to set in your scripts. So LSL operates asynchronously, meaning that the sender and the receiver run on independent schedules. So there's not really a fixed clock tying them together. And that's important to keep in mind for these closed loop designs. So you should always be basing your timing decisions on the LSL timestamps, which are attached to each sample, rather than assuming that the data you just received is from that exact moment. So that's an important point to make sure you're actually accessing the data in real time. Related to that is understanding that this LSL works with this FIFO buffer. So the LSL buffers data on first in, first out basis. So you always get the oldest available samples first, and there's no way to directly request the most recent one. So this is why it's important to set this chunk length and buffer. Um, so, and this is where you apply these changes in the inlet configuration. So it's important that you drain the buffer efficiently as to avoid that it grows over time and to avoid that it introduces lag. And here's we also we recommend to use this pull chunk command to call in your data, which drains the entire, well, rather than the pull sample, which pulls there's is a per sample loop. The pull chunk just pulls all the available samples that are currently in the buffer just at once. And then you can set this one to be at the minimum size, so it comes as small as possible. That said, it's impossible to fix an exact. So if you set the pull chunk to one, so you want one sample at a time, it doesn't mean that it's always going to be coming at one sample at a time. It might come with higher amounts. But here's where it comes the important thing of actually monitoring your buffer. Just so, even though that might vary over time, you just want to make sure that this keeps quite constant so it doesn't increase and most importantly, it doesn't increase over time. So the default buffer length, it's 360 seconds. So it's intentionally large to give you a recovery time from things like a dropped connection or a laptop running out of battery. So that's fine for offline use, but if your inlet dies while the outlet keeps buffering, this 360 seconds of data can become a serious memory issue. So it's important you set that to around 5 seconds as recommended also by LSL. And then for the chunk size, it's where you want to set this to one, as I said. So that's going to give you the smallest possible deliverable from the sender. So that's not always going to be constant, but it's going to be the smallest possible. This is recommended to always have this timing monitor. And just as a final reassurance, the timestamps always remain correct. So regardless of this chunk size or delivery delays, LSL, the timestamps on each sample are always accurate. So even if there's some variability, you can always trust your post-hoc offline analysis, which is what Lab Recorder then handles for you. So quickly to finish up the MATLAB and LSL, here is just a few lines that are crucial for ensuring that. So in MATLAB, you always will need to compile the libraries for the first time, and then you can load them, find the EGI AmpServer stream, and also if you want to find the DIN ones, you will have to add the marker one. Then you set this LSL index. That's here's where you set the max buffer and the chunk size. So here's where you will enter this 5 and 1 that I was mentioning before. And then from there, you will use this inlet pull chunk to just start getting the data and use this TS as your timestamps to actually know if that's to be sure that you are on the real-time data. So same for the Python libraries. It's quite similar, just changes, of course, the language. So in here, you don't have to compile anything. So just do a pip install to have the LSL libraries for Python. And then you set as well the stream. And then here you have the same parameters, just slightly different. So here you would also set your 5 and your 1, and then also use the pull chunk function. So that was all. I hope this information was useful. So I will open this now to discussion if anyone has any questions. So you're welcome to do so. And thank you for listening.
Thanks, Zach. That was great. If anyone has questions, just feel free to put them in the Q&A section, and we'll get through them one by one. While we're waiting for people to add some questions, can you offer any advice for groups that are just getting started with kind of streaming to other applications, like in terms of, the easiest way to start or things that they might need?
Yeah, of course. So the connector itself doesn't require any coding. So it's quite straightforward for you to just, once you have the enabled SDK, to have this app running on your computer. It's all interactive, so you don't really need to customize anything yourself. And then from there, we you have many guidance online of these open source tools like the ones I showed, with many examples, tutorials, and we also can provide a bit of support with that. So you will see that once you're there, you can really play with these open source tools in a really interactive way, and it's made for any user that it's getting started in this world and wants to start to integrate this to their research. So really don't worry too much about the coding if you are maybe not that familiar with it. It's quite user friendly when you use it this way.
And how about any kind of hardware requirements? Are there kind of general requirements for PCs or other things that they may need to make this work well?
Yeah, so the new connector now is compatible with any OS, so you can work with Linux, Mac OS, and Windows. There's some requirements, of course, in old Mac OS and old operating systems that will not be compatible. So just make sure that you're not running extremely old machines. And if you are, for example, for a system 400 that uses old Mac OS, just feel free to just use any other Windows computer. You just need to connect it to the Ethernet switch of the system via a Cat5 cable, and then you just need to set the IP address and subnet mask to be at the same network, so they can recognize each other, and you are free to go. But besides this, there's not really many other requirements. So just also make sure that your amplifier is possibly running like one of the latest firmware versions, the 2014 or 2017. If you are running older versions, just also feel free to reach out to us and we can help you out with this.
Great. And LSL is capable of synchronizing both wired and wireless devices, correct? So someone could connect, say, a wireless, say like a health tracker of some sort, and then sync that via LSL with our network-based connection, right?
Yeah, that's correct. Yeah, so yeah, LSL handles all of these synchronizations that are all over the network. So as soon as they are recognized, all of these wireless or any connected devices, it uses this peer-to-peer time synchronization, and it just works with these clock offsets, which are done frequently, and then it just aligns all of these streams together. It handles this quite well. That's maybe one of the strongest points I would say of LSL for sure.
Great. Last call for any other questions. All right. Well, we will be sharing this via our YouTube channel, and we'll also be sharing things via our social media pages about how you can access this, as well as some of the other documentation that Isaac and the rest of the application support team are working on. If you have questions about any of this as you're getting started, or you run into any issues, please feel free to reach out to the support at magsteamegi.com or whoever you're in most contact with EGI. And with that, we'll wrap up for the day. Thanks everyone for joining. And again, we'll have another webinar on June 3rd, focusing on some of the additional features of the GES 500 and NetStation 6.